Looking at classical algorithm complexity zoo, we have some problem called P problems. They can be solved very easily in polynomial time by classical computers. We also have some NP problems, which are very hard to solve by classical computers. However, in the area of quantum computing, we have a new complexity class called BQP. That's bounded arrow quantum polynomial time. As you can see from the slides, the right dots are some problems falling into NP problems, which means that they are very hard for classical computers to solve. However, they are also BQP problems. And that means using a full power quantum computer, you can solve those problems in polynomial time. And today, the first problem we want to introduce is actually the most famous algorithm, and that's called Shor's algorithm. Shor's algorithm is used to solve a problem called integer factorization. Suppose you have an integer n. We would like to find its prime factors. For example, if you have an integer 15, we can easily find its prime factors, and that is 3 and 5. However, on the top of the screen, we have a very big number here. Can anyone guess what are the prime factors for this number? Well, I guess no, because the complexity of this problem, even for classical computers, is very hard to solve. This is NP problem. And that's why RSA, the public key scheme, is based on this problem. And actually, for the public key, everyone knows the public key, but it's a large number. To get its private key, you need to factorize the public key. And it's, again, very hard for classical computers to solve. The best classical algorithms can solve it in sub-exponential time. However, Shor's algorithm running on a quantum computer can solve it in a quantum polynomial time.